Welcome back, everybody. In this section, we're going to go over 3.3, which is about mixture problems, another kind of broad class of word problems. I can tell you right now that usually people find mixture problems kind of challenging, so we'll want to be careful here. What a mixture problem is like is typically where we have a couple of objects of some kind that are mixed together. For example, it could be a jar of coins that contains both nickels and pennies, or it could be a coffee blend that is made out of two different qualities of coffee that have two different prices. It could be two different investments at two different interest rates. Okay, and what makes it interesting, what makes it a mixture problem is that each of the quantities or things that there is that we're combining, so let's go with the coin one, for example. If you have a jar with pennies and nickels, let's say, you could have a certain number of coins and a certain dollar value for those coins. So each item there, that is each coin, has a value. A penny is worth 0.01 or 1 cent. And also there's the attribute of how many coins you have. For the one about the coffee, that is two different grades of coffee. Each, a high quality coffee may be more expensive, and you have a certain number of pounds of that. And then a lower quality coffee would be at a different price, and then you have a number of pounds of that. So there's these different numbers that we need to juggle in the problem, and that can make it a little challenging. But we'll see that if we're careful, they're not too bad. So let's try with the one that is most probably easiest to visualize, and that's going to be a coin problem. And I'd say it's most easy to visualize because probably most all of us have like a jar of coins or something in our house somewhere, and we can kind of visualize that. So for this first one, it says Edna has $2.10 in nickels and quarters in her backpack. She has 12 more nickels than quarters. We want to know how many coins of each type she has. So the uh, things that we're looking for is how many nickels and how many quarters there are. Again, there's two different things there, but we're only going to use one variable for this. There are ways where we could set this up using multiple variables, but it's simplest, I think, just to do it as one variable. So let's do that, and I'm going to make n be the number of nickels she has. And then we want to put everything else in terms of that. Okay, so she has 12 more nickels than she has quarters. So the number of nickels is 12 more than the number of quarters. So the number of quarters would be n minus 12. That's the number of quarters. Okay, make sure that you make that makes sense to you before we go on further. If she has 12 more nickels than quarters, then, for example, forgetting all the rest of the problem for a second, then 12 nickels would go with 0 quarters, 20 nickels would go with 8 quarters. The number of nickels she has is always 12 more than the number of quarters. Or conversely, the number of quarters is going to be the number of nickels minus 12. Okay, so make sure that that part makes sense to you. Okay, now these two statements are about the number of coins, right? N is the number of nickels there are, the physical pieces of metal, and minus 12 is the number of physical quarters there are, not their value. The value of the nickels is going to be 0.05 times the number of nickels. If you think about it, if you have 3 nickels and they're worth 0.05 each, 3 times 0.05, 0.15. Okay, for the quarters, their value is 0.25 times the number of quarters we have, which is n minus 12. Okay, the last sentence, how many coins of each type she has, that is the part that is just telling us what it is that we need to do. And then the other piece of information we have not used yet is the fact that the total amount of money is $2.10. So that $2.10 is going to be the money in nickels, so 0.05 n, plus the amount of money in quarters, 0.25 n minus 12. Okay, so that's our equation. It's about the value of the money that she has in her backpack. We're going to solve that to figure out how many nickels she has. So let me start by distributing to remove the parentheses. It's 3. Okay, and so we've removed the parentheses, so now we want to combine like terms. If you want to eliminate decimals here, you can. I don't think it's really necessary, but if you want to, you can. Here, 0.05n plus 0.25n will be 0.3n. Okay, we're going to add 3 to both sides. That will give us 5.10 is equal to 0.3n. And then we'll divide both sides by 0.3. So we have 5.1 divided by 0.3rn. And that will be 17. Okay, so remember this is a number of coins. We'd better get a whole number for that. Okay, and then the number of quarters is 12 less than that. So the quarters is going to be 17 minus 12, or 5. Okay, so now we should check and make sure that this makes sense. So let's do that. So 5 quarters would be $1.25. 17 nickels is going to be 85 cents. And so adding that up, we're going to get $2.10, which is what we needed to have happen. Okay, so that's our example of a coin problem. Typically, we have 2 coins, pennies and nickels, dimes and quarters, whatever it is, and we have, of course, a dollar amount for each one, and then a number of coins for each one, and then usually the statement is about the dollar value that it adds up to. Okay, so let's try this next one next. This one is about nickels and dimes. So Paula has $4.20 in nickels and dimes on the floor of her car. She has twice as many nickels as dimes. We want to know how many coins of each type she has. Okay, so to do this, again, I want to try to figure out a variable for this. And while we could go with N for nickels or D for dimes, either way, I noticed that the number of nickels is twice as much as the number of dimes. So the amount of nickels is described in terms of the number of dimes. So for this one, I'm going to make D be the number of dimes. Okay, she has twice as many nickels as she has dimes. So then 2D, that was supposed to come out of D. She has 2D as a number of nickels. Okay, again, this is how many coins there are. The money that she had, sorry about that, Zoom crashed on me again. So we had D for dimes, so 0.10D will be the value of the dime. If there are 2D nickels, there are 0.05 times 2D for the value of the nickels. Okay, and that will actually simplify to 0.10D also. That's interesting. Okay, so then that $4.20 she has, that is going to be the dime money, which is 0.10D. And then also the nickel money, which turned out to be 0.10D also. So then we have 4.20 is 0.20D. Dividing both sides by the 0.20. That will be our number of dimes. That's the same as 42 divided by 2. And that is the same as 21. Okay, so then if there are 21 dimes, there must be 42 nickels, because it says twice as many nickels as dimes. So if there are 21 dimes, that'll be worth $2.10. And then 42 nickels, which can also be $2.10. That would make a total of $4.20. Okay, so there is that. A couple of things just to kind of be careful of with this. They're one smaller, one bigger, is that a nickel is going to be 0.05. That is the value of a nickel. Sometimes I see students will write 0.5 for that. 0.5 would be like a 50-cent piece, which you probably haven't seen, but it needs to be 0.05 for a nickel. Also, and this is relatively smaller, this is not the same as N-I-C-K-L-E. That's not the spelling for a nickel. Okay, so that's it for coin problems. Okay. The next kind of category of problems that you may see are ticket and stamp problems. Here, the story is we have a movie theater that sells two different kinds of tickets. There's an adult ticket for $10 each, and then a child ticket for $7.50 each. And we sell a certain number of child tickets, a certain number of adult tickets, and then we collect a certain amount of money. And based on this, we want to figure out how many of each kind of ticket was sold. So here, instead of being two different kinds of coin, this time it's two different kinds of ticket. One thing that is similar, though, is that each thing, before it was coins, now it's tickets, has a value, in this case, the price of the tickets, and also how many there are. So a quantity plus a price for the adult tickets, a quantity and a price for the child tickets, just like we had a quantity and a value for nickels and a quantity and a value for dimes, whatever it was. Okay. This category of problems is ticket and stamp problems. Years ago, you would see more problems involving stamps, people buying 10-cent stamps and 13-cent stamps. But these days, people mail so few things compared to how it used to be that you just don't mail stuff as much. So there's fewer stamp problems, but they work out the same way as ticket problems will. Okay, so here we have adult tickets for $10, child tickets for $7.50. We want to know how many child tickets and how many adult tickets were sold. So it's going to be both that we need to find. So it's up to us really which one we want our variable to be. I'm going to go with A as the number of adult tickets sold. Okay, and then let me take a look at the wording and see if that's going to work nice for me. It says the number of child tickets sold was 25 less than twice the number of adult tickets. So twice the adult tickets, but 25 less. That will be the number of child tickets. So I'm glad I made the choice that I did. If I had made the variable be the number of child tickets on this one, I think I would have had a harder time figuring out how many adult tickets there are. But since the number of child tickets is described in terms of the number of adult tickets, it's easier if I make the variable be the adult tickets and describe child in terms of that. Okay, so now we have a price for each type of ticket, and we know the total amount of money that was received. That was $2,612.50, and that was the adult money plus the kid money. Okay, so the $2612.50 adult money is $10 for each adult ticket times the number of adult tickets. Sorry about that. Okay, so $2,612.50, $10 for each adult ticket, and $7.50 for each kid ticket. There were 2A minus 25 of those. Okay, so that's our equation. So make sure that that equation makes sense to you, and then let's go ahead and solve it. So I'm going to do this by first distributing to remove the parentheses. So 2612.50, that'll be 10A plus 750 times 2 is going to be 15A. And then in the back, we'll have 750 times 25. And I'll work that out here in a second. So we have 2612.50 on the left side. 10A plus 15A is 25A. And then let me calculate 750 times 25. Okay, that's 187.50. Okay, and then let me add the 187.50 to both sides. Okay, so we have 2,612.50 to add to that, and that ends up 2,800 even as 25A. So then 2,800 divided by 25 will be our A, and that's 112. So 112 adult tickets. Okay, so there were 112 adult tickets. And then the child tickets we're told is twice that, and then take away 25. So 2 times 112 is 224, minus 25 is going to be 199. Okay, so for this one, I will leave it to you to check that that works out. You would multiply the adult tickets, that is the 112, by 10. The 199 would get multiplied by $7.50. Add the two results, and you should get 2,612. Okay, so that was a ticket problem. The next problem is we're mixing together Coke and orange juice. So here it says Shane wants to mix orange juice and Coke to make punch. He can buy orange juice for $3 a gallon and Coke for $4 a gallon. Shane wants to make 28 gallons of punch at a cost of $3.25 a gallon. We want to know how many gallons of orange juice and how many gallons of Coke he should buy in order to make this happen. So for this, we do have quite a bit of different numbers floating around. We have the gallons of punch, we have the gallons of Coke, we have the gallons of orange juice, we have the dollar amount for the end product, the punch, we have the dollar amount for the Coke, and the dollar amount for the orange juice. So that's a lot of different numbers. You may want to organize your information in a table if you like. You can do that. Maybe we should for this one. So we have the orange juice, we have the Coke, and we have the punch. Okay. And then I'm figure out the dollars per gallon for each. The orange juice is $3 a gallon, the Coke 4, and the end product $3.25. And then he wants to make 28 gallons of punch. So we know the end product is the 28 gallons. What we don't know is how much orange juice and how much Coke should be used. I don't want to use a variable like O for my orange juice because that's just asking for trouble, right? Because it looks like a 0. So you could use X. I'm going to use C for the gallons of Coke. Okay, and once we know how many gallons of Coke, we'll know how many gallons of orange juice. Okay, so for the Coke, we'll have C. This will be our quantity. And then there is a total of 28 gallons of punch. If C of it is going to be Coke, then the rest of it, 28 minus C, has to be orange juice. Okay, so now the total cost for the components is going to be 3 times 28 minus C for the orange juice, $3 a gallon for 28 minus C gallons. For the Coke, it is going to be 4C. And then lastly, for the punch, the end product, $3.25 for the whole 28 gallons. Okay, so then we've used up all the numbers, compiling everything into the table there. So let's see if we can determine what has to equal what. Well, the money spent for the orange juice and Coke, that is our last column, those two together have to equal the price for the whole punch. So 3 times 28 minus C plus 4C will be 325 times 28. All right, so then let's go ahead and distribute to remove the parentheses. So 3 times 28 is going to be 75 plus 9, that's 84, minus 3C, there's 4C, and then the right side, 28 times 25 is 91. Glad that came out even. That was lucky. All right, so then negative 3C plus 4C will be a single C, and then 91 minus 84 is going to be 7. Okay, so it looks like 7 gallons of Coke. And then the remaining would have to be 21 gallons of orange juice. Okay, so I know that would total 28 gallons. Let's just check and make sure that the pricing works out. We know the orange juice is $3 a gallon. So we'd have 21 gallons of orange juice at $3. He'd spend $63 on orange juice. The Coke is $4 a gallon. And if he bought 7 gallons, that would be $28 spent on Coke. So altogether 8, 9, 10, 11. And so that's $91 that he would spend altogether. And that's the same as the $3.25 times 91. So it works out 7 gallons of Coke and 21 gallons of orange juice. Okay, so that is a pretty typical mixture problem. Sometimes you'll see others where they've tried to make it sound more technical, where it's like a chemist and it's an alcohol mixture or antifreeze or acids or something. But here, fruit punch, it works out the same. Okay, we have this time volumes of the two different kinds of ingredients, the orange juice and the Coke, and then their dollar amounts. For problems involving acids, sometimes it's a concentration or a strength of the acid, but it works out the same way. Okay, so our next category of problem is an investment type problem. And we've already seen how interest works. We know the formula for simple interest is I is equal to P times R times T. I is the dollar amount of interest that is earned, P is the principal, R is the interest rate, and T is the time. So that's the background information we're going to need on this one. Here it says Bert has $14,000 to invest in two different mutual funds. One mutual fund pays interest at 4% per year. The other pays interest at 7% per year. We want to know how much should Bert invest in each fund if he wants to earn 6.1% on the original investment of $14,000. So first of all, a natural question that comes up is, why would he put some of the money at 4%? Wouldn't he put it all at 7% and earn more interest? Why? So that's a natural question. It makes total sense. And the reason for that maybe is that maybe with the higher interest rate, there's a greater risk of losing his money. And so he's a little risk averse. He doesn't want to take on too much risk for his personal taste. And so he's putting some money in a more safe but lower paying account. And then to get a little bit more money, he'll put some of the money into a little bit more risky but a little bit better paying mutual fund for this. So that's the reason why he might not just put it all at the 7%. Okay. The other thing to know here is we are told that each of these investments pay a certain percentage per year. So all of this is per year. And since this is all per year, for our interest formula, we're going to take T to be 1. So the amount of interest that is earned here is just principal times rate. Because if it's per year, T is 1. Okay, so then he wants to earn 6.1% of the original 14,000. Okay, whatever that is, we'll work it out in a minute. He wants to earn 6.1% of 14,000, and that's going to come from two sources. He's going to get some from the 7% account, and he's going to get some from the 4% account. That money together will give him the total 6.1% of 14,000 that he needs. Okay, let me go ahead and work out the 6.1% right now. Okay, that works out to be $854. So the $854 has got to come from two places, the 7% account and the 4% account. Okay, so once again, we need to pick out a variable for this. I'm just going to go with X for this. This will be the amount of money invested. You don't want to just say amount invested, right? We should be more specific. It doesn't matter which account you choose. I'm going to go with the 4% account. If you chose the 7% account, you can have different looking work, but the same answer. Okay, so X will be the amount of money invested at 4%. And so the amount that comes from the 4% account will be 0.04X. Principal is X, the rate is 0.04, and the time is 1. Okay, so then the amount invested at 7% will have to be the rest of it. So that'll be the 14,000 minus X. This will be the amount invested at 7%. Okay, so 0.07 times 14,000 minus X. Okay, and that's our equation. So once again, we're going to distribute to remove the parentheses, and then combine like terms and go from there. Okay, our left side is 854. For the right side, 7 times 14 is 84. And so that's going to be 840. Okay. And then in the back of plus 0.04x. Okay. Actually, 8,400. Yeah, let me double check that. See, I'm recognizing that there's going to be a problem with this because the 854 minus 840, that will come out positive, but then negative 0.07x plus 0.04 is going to be negative. So this is going to tell me that something is wrong because I need to have a positive value for x when we're done. Okay, so let me just double check my 14,000 times 0.07. And that's 980. I was pretty far off. That's why. Okay. All right. So that was 980. So that works out nicer. So then subtracting the 980 from both sides, that will leave us with negative 126. And then on the right side, we will have negative 0.03x. Okay, solving for x, we'll have 126 divided by negative 0.03. And that works out to be 4,200. Okay, so that is the amount. It's a good thing I wrote it down. That is the amount invested at 4%. So then we'll need to have 4,200 at 4% interest. And so then the rest of it, which is 14,000 minus the 4,200 or 9,800, will be at 7%. So that's the rest of it. And then we can double check and make sure that this works out. Let's take interest that's earned, which is 4,200, and I'll multiply by 0.04. That will give $168 in interest, where the 9,800 at 7% will give $686. And then the total there will give 854, which is what we wanted. All right, so that is the last of the mixture problems. So one thing that you may or may not have noticed, worth noticing, is that on all of these mixture problems, we had kind of a similarly structured equation. On this one with the investments, it was a product, something times something, plus something times something equaling a number. Okay? And then in the previous one, with the tickets and stamps, or this one's actually the Coke one. Let's go with the ticket one. Here we had, once again, a product plus another product equaling a number. The ones with the orange juice and Coke, it was a product plus another product equaling, this time a product, but it worked out to be a number. These mixture problems frequently will have that sort of a structure where we have something times something plus something times something else equaling a number. Okay, and so don't be surprised when you see those turn out. All right, so that takes us to the end of this section on mixture problems. As you can see, there's a large variety of problems, from coins to coffee to investments and Coke, right? So, but a lot of them are very similarly structured. Also notice that even for problems where more than one thing is found, like the amount of money invested in two different investments here, we still did the whole thing using only one variable. And you'll find that that's true, that that's possible for every problem within this. Like I said, that takes us to the end finally. Let me know if you have any questions, and then have a great day.